Hi and welcome to this lesson on audio noise and spectrograms. Spectrograms are incredibly useful tools in sound processing. They show how the frequency content of a signal changes over time, making it easier to identify and isolate noise, understand speech patterns, and analyze the audio in detail. Spectrograms allow us to pinpoint the frequencies responsible for unwanted noise, remove them, and improve the quality of our audio files. But what exactly is this noise? Noise refers to any unwanted sound present in an audio recording and impacts the clarity and quality of the file. This includes sounds from the environment where the recording occurs, such as traffic, construction work, wind, birds, or people talking in the background. Other types of noise can include electrical noise from recording equipment, hum from power lines, or even random noise generated by digital processing. As you've probably heard, our audio file has intense background noise. Background noise can interfere with the audio content by masking critical frequencies and making it difficult to understand speech. Like humans, speech recognition systems also experience difficulties recognizing a noisy sound. Most tools have built-in noise reduction systems and are trained to handle such situations using audio, including noisy speech files. Noise in the audio file, however, can still hinder the accuracy of the transcript. So, how can we handle noise in the files manually? A good approach is to first visualize this noise and see its frequencies. Let's do so with our audio file in Jupyter and see where these hidden frequencies are. I'll copy the code I used earlier, paste it into a new cell, and execute it to obtain the file's waveform. Good. When we play the file, we notice that the first 1 or 2 seconds consist only of noise. My name is Ivan, and I am excited to have you as part of our learning community. On the waveform, this is visualized just before the speech begins, marked by a drastic change in the graph. We can identify the noise waveform by observing the amplitude of each sample. Furthermore, the file's last 1 or 2 seconds contains speech without noise.
IT and communications.
This is useful because it allows us to see the signal in this region and compare its graph to the rest of the audio, helping us identify which frequencies need to be removed. We mention frequencies quite often, but here we can see only amplitudes, right? So how can we use this information to obtain the dominant frequencies in the audio file? Well, this is where the short-time Fourier transform comes into play. Do you remember what it does? The short-time Fourier transform enables us to convert the representation of an audio signal from the time-amplitude domain to the frequency domain, allowing us to analyze the audio file's frequency components. This makes it possible to identify and reduce noise based on its frequency characteristics. Typically, speech recognition models perform this transformation internally as part of their processing pipeline, so we usually don't need to do it manually. But we'll demonstrate how to use STFT to visualize a spectrogram, an essential skill when working with audio data. Visualizing the spectrogram allows us to see the dominant frequencies and the frequencies of any noise we want to remove. We'll do that in the next lesson. See you there. Hi. Let's see how to make spectrograms in Python with the help of the short-time Fourier transform. We'll use Librosa and its corresponding function, STFT, to compute a short-time Fourier transform. In a new cell, type S, which is a standard naming convention for a variable storing a spectrogram obtained with STFT. Then, after the equal sign, type librosa.stft. In parentheses, put the variable containing the audio data of our file. Remember, this variable contains the time amplitude representation of the sound. Therefore, this is the representation we'll transform into the frequency domain. Let's execute. The function breaks the audio signal into short overlapping segments and applies the Fourier transform to each segment, resulting in a complex valued matrix stored in the variable S. Each value in S tells us how strong a particular frequency is at a specific time. But looking at these raw numbers can be confusing. We need to convert the amplitude values in S to decibels to make it easier to understand. They are part of a scale that represents how humans perceive sound by giving us a clearer picture of the loudness of each frequency. Okay, let's do that using Librosa once again. Create a new variable and call it SDB, deriving from decibels. Then type Librosa.amplitude to decibels, a function that will do the conversion for us. It seems that Librosa took care of everything. We must pass two arguments here, so let's break down what's happening. First, the short-time Fourier transform calculates the frequency components of the audio signal and stores them in S. The values in S are complex numbers which have two parts: the amplitude, which is the magnitude or length of the complex number, and the phase, which tells us the timing or position of the wave. But since we're only interested in the amplitude, we use ABS-S to extract it. The ABS function calculates the absolute value of each complex number, which gives us the amplitude for each frequency in the audio. Now, the amplitudes can vary greatly and aren't directly related to how we hear loudness. For example, an amplitude of 1000 doesn't sound 10 times louder than an amplitude of 100. So we need to convert these values into decibels, which are easier to understand. The Librosa amplitude to dB function converts this for us, making the values more useful for analysis. Ref equals to np.max ensures the highest reference value is 0 decibels. Let's check that out by calling the function separately. See? Setting the reference level to the maximum value in the amplitude spectrum normalizes our values. This means the loudest point in our spectrum will be 0 decibels, making it easier to understand and compare. It simplifies understanding the dynamic range by showing how quieter other parts are relative to the loudest part. This normalization aligns with standard audio analysis practices, making the data more intuitive and consistent for interpretation. Okay, good. What's left is to visualize the spectrogram. I'll create a new plot figure with a specific size of 12 inches by 4 inches. Then I'll use Librosa.display.specShow to display the spectrogram. In the parentheses, I'll use data equals SDB to show the decibel scaled spectrogram. And SR equals sample rate is used to define the sample rate of the audio signal and label the time axis. To set the x-axis to represent time, use x-axis equals time. The x-axis parameter expects a string value, and one valid option is time, which configures the x-axis to display what we need. Y-axis equals log is used to set the y-axis to a logarithmic scale, commonly used for visualizing frequency data. PLT.colorBar will add a color bar to the plot to indicate the spectrogram's decibel levels. The following value of the format parameter will display the color bar labels with no decimal places. We're almost done. Let's define the graph's title and XY labels as spectrogram, time, and frequency. Finally, we'll use plt.show to display the spectrogram. All right, I think we're ready to execute. Excellent. Now we can analyze what we see here. On the left y-axis, we have the frequency range from 0 to about 16,400 Hz, covering all audible frequencies, with lower frequencies at the bottom and higher frequencies at the top. The right y-axis displays amplitude in decibels ranging from -80 decibels to 0 decibels. Here, 0 decibels marks the peak amplitude, while -80 decibels indicates much quieter sounds. The more yellow the colors, the louder the sounds. Human speech typically falls between 80 and 250 Hz for fundamental frequencies, with harmonics extending to 8,000 Hz or higher. Notice the yellowish tones between 64 and 256 Hz? Their color indicates that they are the loudest in the recording. Additionally, they coincide nicely with the fundamental frequency of human speech. We can conclude that this is primarily where speech occurs in the recording. We hear the background noise in the file during quieter intervals where no speech is recorded. These regions show various frequencies, though not very loud. Furthermore, the audio's last 1 or 2 seconds contain almost no noise. Focusing on this part of the spectrogram reveals the missing noisy frequencies compared to the rest of the graph. These are mainly in the range of 512 to 2048 Hz and higher. We can try removing some of these frequencies from the whole file and hear if it sounds better. Of course, we can't remove all sound of these frequencies because in this case, we would also be removing some of the speech. Actually, we don't need to do that manually, you know. Python has its own methods for dealing with noise. Stay tuned for the next lesson where we'll explore this topic further and work on filtering out some of the noise. See you then. Welcome to another exciting lesson on working with audio. Here, we'll demonstrate how to manually increase an audio file's clarity by removing some of its noisy frequencies and emphasizing frequencies that bring more information to the speech recognition model. Let's begin. In our previous session, we generated a spectrogram to analyze the audio file's frequencies, identify the speech segments, and examine the frequency range of the background noise. Let's now see how to deal with this noise to improve the speech-to-text results. One common approach to handling background noise and improving a speech recognition system's WER and CER results is to emphasize the higher frequencies in the audio and de-emphasize the impact of frequencies that potentially contain noise. High-frequency components of speech often carry essential information for understanding and differentiating words. Models tend to perform better when processing higher frequencies because these frequencies contain critical speech details, such as consonants, that help distinguish between similar-sounding words. Focusing on these higher frequencies can improve the model's ability to accurately recognize speech, even in noisy environments. So how can we do that? As always, Librosa provides a straightforward solution for this task as well. The package allows us to directly apply a pre-emphasis filter and enhance these high-frequency elements, making them more prominent and easier for the speech recognition system to detect. This process helps reduce the impact of lower and mid-range frequency noise, thereby increasing the speech signal's clarity and improving the transcription's accuracy. Librosa offers a collection of audio processing effects that can enhance and manipulate audio signals in various ways. One function in this collection is pre-emphasis, found in the Librosa.effects collection. It's used to apply a low-frequencies cutting filter to an audio signal, exactly what we need. In a new cell in Jupyter Notebook, I'll create a new variable for the filtered audio we're about to process. I think signal_filtered is a fitting name for it. After an equal sign, I'll call the pre-emphasis function and open a set of parentheses. The function expects 2 parameters, the audio data input, which in our case is named audio signal. The second one is a coefficient determining the degree to which the high frequencies will be emphasized, with a higher value corresponding to higher emphasis. The default value in many implementations is 0.97. This number balances the need to emphasize the high-frequency components sufficiently for clarity and to maintain enough of the original signal to avoid distortion. So let's use this value here. I'll employ the sound file library. Recall that we aliased SF to call the write function and save the processed audio file in a WAV format. Store the path to the file in a separate variable called output file. Let's execute this cell and filter our audio. To compare the newly obtained file with the original, I'll employ the well-known method from earlier and extract two simple media players that allow us to play both files. Okay, let's play the original audio.
My name is Ivan, and I am excited to have you as part of our learning community.
Press the play button to start the modified one.
My name is Ivan, and I am excited to have you as part of our learning community.
There's indeed a noticeable difference between the two files. We can hear a reduction in noise and a clearer emphasis on the high frequencies. While the audio may not sound significantly better, it's likely more apparent to the speech recognition model. Now, let's create a spectrogram for the new version of the file and compare it to the original version. This way, we'll hear and see the differences between the two. I'll use the same code as before, but apply it to the new version of the file, which is stored in the variable signal filtered. Replace this with the original audio signal version and adjust the code. Then run it. Great. There's a noticeable difference between the two visualizations. In this one, we can observe less intense yellow colors, indicating a slight reduction in the loudness of specific mid and low frequencies that were stronger in the original version. The voice parts, however, are still distinguishable, though now a bit darker. Focusing on the higher frequencies, we notice they are slightly more yellowish than before, which makes sense since we expect the new file to emphasize these frequencies to help the model better recognize the speech. Let's test if that's the case. We'll transcribe this updated version of the file using the same function we defined earlier. Just insert the new audio file we generated a few code cells ago into the parentheses. Interesting. The two words that were incorrectly transcribed in the previous version, turn and seem to be correctly recognized here. If you recall, they were transcribed as term and in the previous version. While it's not in the correct past tense, which should be turned, the current version still makes more sense than before. Even for the human ear, distinguishing between turn and turned can be difficult. But here, we can highlight the fact that the model didn't realize that using the verb in the past tense makes more sense. This suggests that while adequate for basic transcription tasks, the speech recognition library may not have the same level of contextual understanding as more advanced models. We'll demonstrate that soon enough. Okay, to verify the current improvement, let's apply the well-known evaluation metrics WER and CER and assess the results quantitatively. I'll copy and paste the code from above and place the variable containing the new transcript here as an argument. After rearranging the code, we can run the cell and wait for the evaluation results. Okay. WER shows 0.3220, while CER indicates 0.0773. This is indeed better than the previous results, which were 0.3390 for WER and 0.0884 for CER. Great, so it does work. Please note that various additional methods exist to clean audio file noise beyond the pre-emphasis function. For example, Librosa's trim function from the effects collection can remove silent or noisy sections at the beginning and end of an audio file. The HPSS function, or harmonic percussive source separation, again from Librosa, can separate harmonic and percussive components of an audio signal. This can be useful for isolating speech from background noise even more precisely. The Adjust for Ambient Noise function from the speech recognition library can adjust the recognizer's sensitivity to ambient noise, helping to filter out background sounds. So, pre-emphasis is a valuable tool that often improves results, but it's not the only solution. Additionally, some models are trained so well on noisy audio that they can handle problematic files with minimal intervention. In our case, while noise cleaning with pre-emphasis improved the results, issues like the lack of punctuation and using wrong tenses remain. Therefore, we'll introduce another method for speech-to-text that is transformer-based and generally more efficient, even without extensive manual noise cleaning. See you in the next lesson where we'll employ Whisper AI for speech recognition. Can't wait.